Here she is.
I'm not late. I don't know.
I know. You can start now. All right. I hope you all enjoyed President's Day as much as I did. There should be more of them, but anyway. Homework number 4 is due this Friday, so just want to remind you guys about that. So we're just going to continue this section 14.4. We're talking about what's called a tangent plane, and then we're going to see how this tangent plane can provide us with an approximation for the value of the function. So, again, let me do a little drawing here, x, y, and z, and so let's have some kind of surface here. This is our surface, and let's put a point on the point P on the surface. All right. Now, if we can cut this surface in 2 ways. We can cut it along the x direction, and that'll give us a curve along our surface. We can call that C1, that curve. We can also cut our surface along the y direction, going through the point, and that'll give us a curve that we can call C2. And then each one of these curves basically has a tangent line. So we have a tangent line going this way here for C1. We'll call that T1. And a tangent line going kind of sort of like this for our second curve, and we call that T2. And then these 2 straight lines that are going through that point form a plane, okay? So the 2 tangent lines form a plane. And we call this the tangent plane at point, in this case, let's say it's at point P, which has, let's say it has the coordinates x0, y0, and z0, all right? And then we have an equation for this tangent plane that you guys need to remember. I'll put an asterisk by that. Equation of the tangent plane. And that's given by z minus z0 equals partial derivative of f with respect to x. And that's evaluated at x0, y0. And then we have our variable x minus x0. Then we have the derivative with respect to y, again evaluated at x0, y0, and this time it's multiplied by y minus y0. Okay. All right. We did an example of, we're given a surface and we found the tangent plane, did that last time. Now, the fact here about this tangent plane is this. This tangent plane at point P is the plane that most closely approximates the surface at or near that point P. So let me write this down. So the tangent plane at some point P is the plane that most closely approximates the surface at that point P. Okay. So what we're going to be able to do then is, since this tangent plane is so close to the actual surface, for values that are close to that P, we can use the equation of the tangent plane to obtain approximations of the function value, all right, because it's close. So let me put this here. So we can use the equation of the tangent plane, to provide us with an approximation of the value fxy. And of course, this is our surface value. This is the z surface value, the z coordinate. All right. I want to just show you one thing here. Let's see. I think it's this one. Okay. All right. And let me get this so you guys can see it. All right. What you see in blue here, let me move this around a little bit. Ooh, and it really jumps, I noticed with this. The blue here is our surface. So the surface is really curving upward. And right down here, this, I guess it looks like a purple dot, this is the point on the surface. The yellow plane that is coming out from that is the tangent plane at that particular point. Okay. All right. Now, let me see if I can get it to a place that let's try this. Okay, let me look here if we can zoom in on this. So what this thing is doing now is it's getting closer and closer to the point. It's zooming in on it. So I'm going to zoom in again and again. Now, here we're very close to the point P, and if you notice here, now that blue is that portion of that really curvy curve or surface, but when we get close, the tangent plane actually isn't that far off from the surface. And we can zoom in even closer, so where we're getting even closer to the point. And here they're almost laying just right on top of each other. And then if we zoom in again, where we're getting real close to the point, they're almost indistinguishable from each other. So when you're really close to that point, that plane is very, very close to the z values. It gives you the z values of the surface. Okay. Okay. Now, let me rewrite the equation of the tangent plane. Here we had it written as z minus z naught. So I'm just going to, all I'm going to do to this is actually put the z naught over onto the other side of the equation. So it can be written as z equals z naught plus partial derivative of, with respect to x at x naught, y naught times x minus x naught plus the partial of y at x naught, y naught times y minus y naught. All right? Okay. And then remember here that this z naught is really the, remember, z is equal to f at x, y. So z naught is really the function value at x naught, y naught. Okay, so we can replace the z naught with that. Now, this right over here, this is a linear function. It's linear because we have x and y, but they're only being raised to the first power, all right? So therefore, this is a linear function of the variables x and y. Okay. Now, this value here of z is very close to the actual surface value when we're close to the point. I'll put that in quotes here. This is close to the actual let's say the actual z equals fxy, all right? Oh, you know what? Okay, never mind. At around near the point P. Okay. All right. So what we have here then is this right side here is a linear, because it's a linear function, it's a linear approximation of our surface. The right side is a linear, again, it's an approximation. It won't give us the exact surface value, but it's a linear approximation of our surface. And so, because it's a linear approximation, we can give it a couple different names. One name we can call it is the quote-unquote linearization of our surface, fxy, at the point here is y naught, x naught, y naught. Actually, in the book, we have notation for this, and so I want to put an asterisk by this formula that I'm going to put here. We put capital L for linear, and it's a function of x and y. And this linearization, then, all I'm going to do is put what I have here on the right side of this equation. So this linearization of our surface is this: f at x naught, y naught, plus partial derivative with respect to x, evaluated at x naught, y naught, times x minus x naught, plus the partial with respect to y, again at x naught, y naught, times y minus y naught. Okay. So you'll want to be familiar with the fact that this is this is basically the equation of the plane. Okay. Another name that the text gives for this is the linear approximation of the function. So let me just put that down here. And we're going to go through an example of this. Another name is the quote-unquote linear approximation of f at the point x naught, y naught. Remember with this, we're talking about a specific point where we have a specific tangent plane, okay, and where we have specific values for our fx and our fy. Okay, so this is leading up to this, a fact here, it's actually a theorem, So the theorem is this. If the two partial derivatives are continuous, and that's what we're going to have with the functions that we look at. Oops, I'm getting ahead of myself. If the two partial derivatives, fx and fy, are continuous at the x0, y0, then the function is called differentiable. Then the function f of xy is called, quote unquote, differentiable. And here's the point that I want to get across, and this linear approximation is a good approximation of the function value. And this linear approximation is a good, and I'll put that in quotes because that means it can get really close to the actual value. It's a good approximation near, and again, it's near that point of x0, y0. Okay. So I think we really need to do an example here to see how this can work in an actual problem. So let's just look at this example here. Let's have our function be z equals the square root of x squared plus y squared, or we can write this as f of xy equals the square root of x squared plus y squared, all right? And we're going to find an approximation, find a linear approximation near the point 3, 4. So that's our x0 and that's our y0, 3, 4. All right. So what we have to do here is we have to get, remember this is our linear approximation here, we have to get the fx and the fy of our function, and then we also have to plug in the particular xy values. Okay, because we're going to get a number here, we're going to get a number here. Okay, so let's go on and do that. So let's find fx first of all. Now remember, for fx, that means we're treating y as constant. All right, we're going to have to be using the chain rule here with this. So this is going to be, remember, our function is actually x squared plus y squared raised to the 1/2 power. It's a square root. So we bring the 1/2 down. We decrease the exponent by 1, so that's x squared plus y squared to the -1/2 power. And then we have to use the chain rule to multiply by the derivative of x squared plus y squared. But this is only with respect to x. Y is constant. So x squared plus y squared, its derivative with x is going to be 2x. All right? And then let me just simplify this a little bit. Notice the 2's cancel out here, so we get x, and then let me put the square root on the bottom in the denominator over the square root of x squared plus y squared. Okay, that's our fx. And so at our point is 3, 4, then the value is equal to what? Let's plug in 3 for x and 4 for y. We're going to get 3 over the square root of what? 3 squared plus 4 squared. Well, those are very nice numbers to have selected because that's going to be 25, which is 5. So that therefore our value of our fx is going to be a fraction 3 over 5. Now when we get fy, we go through a very similar process with this. Here x is constant. And we're going to again use the chain rule. We're going to get 1/2 x squared plus y squared to the -1/2 power. But this time, when we do the derivative of the inside, we get 2 times y. So this simplifies now to y over the square root of x squared plus y squared. And then we find its value at 3, 4. And we're going to find that its value is 4/5. Okay, because the y value is 4. All right. Now let's see here. What else do we need to get? Let me just write out the linearization here. Lxy is equal to f at x naught y naught plus fx times x minus x naught plus fy times y minus y naught. All right. So I think what we now have to get still is we have to get this, the value of the function at 3, 4. So that was going to be the square root of 3 squared plus 4 squared, which is just going to be 5. So we get our Lxy, linearization, is going to be 5 plus, now we had determined that our fx value earlier was 3/5, and now this is going to be x minus x naught, so that's going to be x minus 3. And then our fy we determined was 4/5, and y minus y naught is y minus 4. Okay. You can leave it just like this. You don't have to distribute it. That's fine. Okay. Now, so this is our linearization. So let's figure out how good it is. Okay. So let's look at the point where xy is equal to 3.04 and 3.98. Okay. All right, so what we have to do is we basically plug in, we're going to plug in, this is our x, this is our y, and we're going to plug that into our linearization. So that's going to give us 5 plus 3/5. Now, 3.04 minus 3 is going to end up with 0.04 in the parentheses, plus 4/5. Now, 3.98 minus 4 is going to be minus what is that going to be? Minus 0.02, right? Okay. And then let's do some arithmetic. Let's get it all over the denominator of 5. So that's 25 over 5 plus 3 times 0.14 is 0.12 over 5 minus 0.08 over 5. So this all combines to 25.04 all over 5, and that equals 5.008. So that's our linearization of the actual value of the function using that formula. Now, if we actually go in and plug in, so we look at the square root, what is it? The square root of x squared plus y squared, so we actually plug these in, 3.04 squared plus 3.98 squared, and we do the square root, what we're going to come up with is 5.008193. All right? So this is pretty good, actually. It agrees all the way to the third decimal place, so then it's off after the third decimal place. So it's a very close approximation to the actual function value. All right? And I can imagine that something like this would be useful in computer operations, I would think. If you're talking about doing all kinds of calculations, if you can reduce the number of calculations, it might be worthwhile, okay? Because basically this calculation here, I guess, on a computer can be a little bit more time consuming, we're squaring something, then we're doing a square root, so however long that takes the computer to do that kind of thing. Up here, it's basically just plugging in this very linear thing. There's a very simple arithmetic operation to get an answer which, if we consider the answer to be good enough, close enough to what it actually is. Okay, I'm just trying to give you guys a good reason for doing this. Okay, all right. So this is how, so you might have a problem or two in homework where you're asked to get the linearization of a function of a surface, and this is the process that you go through. Okay. Question on this before we go on to differentials. Just remember the formula that I put an asterisk by. All right. So that tangent plane gives us a good approximation, usually to the actual surface. So what we're going to look at next here in this section, this is the last thing in this section, is the topic of what's called differentials. Okay. And there's going to be a relationship with this to our tangent plane function that we just saw. Now, let's try to remember something from first semester calculus, where we have a function of one variable, and let's just say it's y equals f of x, all right? Then you were introduced to this thing called a differential, and you use, of course, whenever you do a u substitution, you use the differential when you do a u substitution, okay? You may not think of it that way. But here, dy is equal to the derivative of our function times dx, all right? And these are differentials right here, this and this right here, okay? Now, dx can actually have, in theory, any number value, where dx can take on any number value. All right. Okay. Now let's look at the function of two variables, and we're going to get a very similar kind of equation here. Okay, so this is going to be, say, z equals a function f of xy. Okay, so now we're going to get dz, but remember, with this thing, we have two partial derivatives. We don't just have a single derivative. For some reason I want to do that. Two partial derivatives. So this dz then is going to equal the partial with respect to x of our function times dx plus the partial with respect to y of our function times dy. This dz has a name. It's called the total differential. All right. And again, dx and dy can take on any number value, where dx and dy can take on any real number value, not complex, any real number value. What? In other words, dx and dy, in other words, we could, for whatever reason, decide that dx is 3 and dy is 4. It depends on the context. But we can replace dx with some number and we can replace dy with some number. No. Mm-mm. All right. So I want to, this formula here, right here, I want to put an asterisk by that, something we need to remember. All right. And I want to contrast that equation. That's for the total differential. I want to contrast this with the following. Contrast with, instead of dz, I want to put delta z. Now, delta z is the change. Delta represents change. This is the change in the z value. And more importantly, I should put here in front of, it's the actual change in the z value. So let me get this up higher. So what this is, okay, this is going to be our function applied to x plus some delta x, y plus some delta y, take away minus the function just applied to x and y. And let me just show you a little picture of this, of what I'm talking about. Okay. In fact, I think I'll just, instead of rewriting it, let me just put this up here. Get rid of this other stuff. Okay. This is what we're talking about for delta z. So we have our x, y, and z axes. And say we have some point down here on the xy plane. We pick a point. That's x naught, y naught. And then that point, we go up, and that corresponds to z naught, which is on the surface. So we have a, oops, where are we here? No, this is my x naught right here. And we go up and hit our surface, and that's the z value corresponding to that. Now what we do here then is we want to look at a new set of x and y values. So I move delta x along the x-axis to get my new x value, x naught plus delta x, and I move delta y along the y-axis to get my new point, y naught plus delta y. Okay, now I have my new point right there on the xy axis, and I draw a vertical line up, and I'll get a new point on my surface. Now the difference of the values of these two f values, that's my delta z. That's my actual difference in my function value. So this difference here is delta z. And what it is, this is my function at x naught plus delta x, y naught plus delta y, minus the function at x naught, y naught. Okay, we just subtract them. Okay, and that's our actual change. Oops. Okay, here we are. All right. Let's look at an example of what we're talking about here. Example. Okay, say our function is this. We're given that z is equal to x squared plus 3xy minus y squared. Okay. All right. And what we want to find here is, first of all, we want to find dz. Let's do that first of all. Okay. dz, we know, is equal to fx times dx plus fy times dy. All right. So let's get fx and fy. fx, well, what's fx going to be? Somebody might want to hazard to, y is constant. Okay, 2x, x squared, And then, let's see, what do we have? Y is constant, so therefore this will go to a 1. So that's 3y. And then, oh, wait a minute though. What about this here? Yeah, it goes to 0. So did you say 2x plus 3y? Okay. So that's fx, and then fy. X is constant. Let's see. X is constant. So what? 3x minus 2y. Exactly. All right. So therefore, dz is equal to parentheses 2x plus 3y times dx plus 3x minus 2y dy. All right, we've got that part of it. Now, before I go on, I want to say this, that this differential value of dz can actually give us a close approximation to the delta z value. Can give us a close approximation to delta z. With delta z, we actually have to do all the number crunching to compute it, all right? With dz, we have a lot less number crunching, and we'll show that here in this next part. So, part B, let x change from 2 to 2.05, and let y change from 3 to 2.96. All right. And what we're asked to do here is to compare the values of the dz and the delta z. Okay. Now this means that we actually have to plug in some numbers for dx and dy here, okay, to figure out what dz equals. We're going to get a number for dz. Now let's look here. 2 is changing from 2 to 2.05. So what's our delta x, or change in x? 0.05? That's our delta x. 3 is changing from 3 to 2.96. So what's our delta y? Negative point, what did you say? Negative 0.04. Okay. So that's our delta x and delta y. And now we're also going to want to let dx and now here we're going to let dx be equal to that same value and dy equal to that same value. So therefore we're going to let dx equal to 0.05 and dy equal to the minus 0.04. All right. Okay, so let's first of all figure out what dz is going to be. Now dz, we had figured out was, let me rewrite it here, 2x plus 3y times dx plus 3x minus 2y times dy. All right, we're going to replace dx with 0.05, dy with negative 0.04. Now, what are we going to plug in for x and y here? No, we're going to go with the original value, Nikesha. We're going to go with the 2. We're going to go with the 2, and we're going to go with the 3. Okay? So we're going to go with, for x, we're going to plug in a 2. For y, we're going to plug in the 3. X, the 2, y, the 3. So let's figure out what our dz value is then. So dz is equal to what? 2 times 2 plus 3 times 3. So what is that? That's 13, I think, times 0.05 plus, okay, then 3 times 2 minus 2 times 3, well, that's 0, times minus 0.04. I'm just plugging in the numbers. And so this equals 13 times 0.05, which is a value of 0.65. Okay. So that's the dz. Now let's calculate what delta z is. What delta z is the actual change in the function when we go from 2, 3 to the other two values. So it's going to be the value of the function at, first of all, the new values, 2.05, comma 2.96, minus the value of the function at 2, comma 3. All right. Now I'm going to leave out all the number crunching, and this is equal to 0.6449. Okay. But of course, there's a lot more arithmetic. So let me just put down here, there's certainly lots of arithmetic with that calculation. But what we get here for our actual difference, the change in the z value, is we get something that's very close to a much simpler computation using the dz. Okay. So again, I would imagine computers like simpler computation. Well, so do humans actually too. So this is an example of something where you'll have this kind of problem where you want to calculate dz, and maybe you'll be asked to calculate delta z. You'll have calculators so you can figure that out. Okay. Question on this other thing, this dz versus delta z. Okay. All right. Then there's the other thing here is the fact that let's just look if our function is a function, say, of 3 variables. So we have, and this is the last thing in this section, we have a similar formula for functions of 3 variables. Okay. So this is where we have, say, w equals a function of x, y, and z, 3 variables. Okay, first of all, let's look at the linearization. The linearization at, let's say, the point A, B, and C. What this is the following. It's basically our function value at A, B, and C, plus, now we have 3 partial derivatives. We have an x, a y, and a z. So then it's going to be the partial derivative with respect to x. Again, we plug that in at ABC times x minus the a value, x minus a, plus, and now we do the fy, compute its value, and then that's times y minus b. Now, we also, in addition now, what's different is we have an f with respect to z value, again at a, b, and c, and this one is being multiplied by z minus the c value. Okay. So the only thing different here is that we have this additional term here with the third partial derivative. Okay. And then we have a z here, z minus c. The other thing then, a similar formula then, is the one for the total differential. That's going to be we'll call it dw, is equal to the following. The derivative with respect to x times dx plus the derivative with respect to y times dy plus the derivative with respect to z times dz. So again, it's similar to the other one. It just now has this extra term here corresponding to the third variable of z. Okay. All right. So that's section 14.4 about tangent planes and differentials. Yeah. We'll just get started with this, and we'll first take a break. The next section has to do with the chain rule, and I really like the way it's presented in the textbook, and so I'm going to use that because it's it relies on a nice picture diagram, and once you get the hang of the picture, you don't even need the picture anymore, but it starts out that way. So this is, of course, going to be a generalization of the chain rule that you know from a single variable function. So this is section 14.5, chain rule. And so we're going to look at basically three different kinds of instances in which we're going to be using the chain rule. So let's just recall from single variable calculus that if y is a function of x, and x in turn is a function, say, of t, then dy dt is equal to dy dx times dx dt. Chain rule from single variable calculus. Of course, the interesting thing about the chain rule, I think, is that it's as if these dx's can cancel out like you're doing just regular arithmetic with them, and you get dy dt on both sides of the equation. Now let's look, of course, at functions of more than one variable. More than one. And I think we'll look at this one and then take a break. So I'm calling this case 1. Now here we have a variable z that's a function of x and y. So z is a function of x and y. And x is a function of t, g of t, and y is a function of t, h of t. And what we want to get here, we want to get dz dt. Now this is where we have this tree diagram, which I think we're going to use for all of these cases, which I think is extremely helpful. Okay, we basically have here like a hierarchy of variables, if you want to look at it this way. We've got z at the top here. Then below it, we have these intermediate variables, x and y. And then below x and y, they're a function of this single variable t. So in this diagram, we can basically take z at the top, it's a tree diagram. Z is a function of x and y. So we're going to branch off from z, x, and y, like that. Right? Now, then x is just a function of a single variable, t, like this. Y is a function of a single variable, t, like this. All right. Now, what we do to find dz dt is we follow all the branches leading from z to t. Follow all the branches going from z to t. All right. So what we have here, so here's our first one. Now this branch can be considered the partial derivative of z with respect to x. After all, that's what we're talking about here. It's a partial derivative because z is a function of two variables. It's not a single derivative. Over on this right branch, z leading to y, again, it's the partial derivative of z with respect to y. Now let's go to the other two branches. X is a function strictly of t, so here for the derivative, I don't need to use the partial notation, I just use the plain d notation. And y is a function just of t, so I use the d notation. Okay, now I want to follow all the branches going from z to t. So we draw the t, we draw the various derivatives that pertain to each of the limbs of the tree. And so we have this, dz dt is equal to this. Well, let's follow the left-hand branch. We've got delta z, delta x, and then we move down times dx dt. That's the first branch. Then we put a plus sign, and now we move down the other branch. dz dy times and dy dt. And that's our answer. That is our chain rule of that derivative. Notice here that this is a full derivative because we only have a single variable t here. So this is a full derivative with d instead of that delta thing, because we ultimately we only end up with a single variable t. Okay. And I could just as well have, instead of writing z at the top, I could just as well have written f at the top. So let me just indicate this. There's more than one way to write some of these things. So this diagram could also have been written with f at the top, a function of x and y, t and t, and then this branch would have been d delta f, delta x, delta f, delta y, and this would still be dx, dt, dy, dt. And I could have then gotten df, dt similarly. Okay? All right. Okay. One little comment, then we'll take a break. Let's actually look here. Let me rewrite this, the first one that I wrote down. I'm just rewriting it. dz dt equals delta z delta x times dx dt plus delta z delta y dy dt. Okay, just rewriting it. Now, the real magic, really, I mean, the one who developed these differentials, I think that was Leibniz. If we multiply everything on both sides of this by dt, dt is in the denominator, dt, so multiply by dt, we get this. Now we just get dz equals delta z delta x times dx, no more dt down there, plus delta z delta y times dy, no more delta t there. And notice this formula right here that we got from doing that, that's the same as the total differential formula that we just had in the previous section. So this becomes the total differential formula. Just by multiplying everything by dt. Or you could look at it the other way. You could start with the total differential formula, divide everything by dt, and you get the chain rule. Shall we take a 5-minute break?
I was earlier, it was 11:30, so I know. You don't think I'm being rude?
Okay, I do appreciate that. Otherwise, what I think in my crazy mind is, well, she's just had it up to here and can't take it anymore. All right. Yeah. Mm-hmm.
I noticed there's an answer to problem 34, but I don't think it's
Oh, great. That's interesting, Tom, isn't it? Let's get the book out.
the hand looks like it goes along with problem 34.
Oh, but I don't assign problem 34. Well, then I guess we don't have to, then I'm certainly not going to make you do it, but what about, I wonder if that was a typo. So, 14.2. I do appreciate you letting me know this, believe me. Okay, 14.2, so we're looking at 33 and 34. Oh, yes. Oh, yeah. So, let's see. Well, determine the set of points such the function's continuous. We'll just go with 33. Okay, that's fine. 33 is fine. In fact, yeah, just going with the natural log. That's no problem. Okay, thank you.
Of course.
Oh, that's my book. That's yours. All right. Let me put it up here. Okay. I give a hint for a problem I don't even define. Annalise says thank you. All right. So hopefully you got all that. Sorry about that mix-up on the homework thing. Thanks to Tom for noticing that. All right. So what I want to do here, let's just do a concrete example here with the chain rule. And here's our example. Okay, z is equal to x squared times y plus 3x y to the fourth, where x in turn is equal to sine of 2t and y is equal to the cosine of t, okay? And we're asked to find dz dt, and more specifically, we're asked to find its value when t is equal to 0. Okay. So first of all, let's just draw the tree diagram. So our top variable is z. It's a variable of x and y, and in turn, x and y is a variable of just t. Okay? So this is going to be dz, delta z, delta x, delta z, delta y, dx, dt, dy, dt. Okay. So let's see. So therefore, dz dt is going to be, well, let's just write something, delta z, delta x from the first branch times dx, dt plus delta z, delta y times dy, dt, just drawing down from our tree diagram. And let's figure out, of course, what these are here. Okay, this one here, delta z, delta x, okay, y is going to be constant. So here's our function here, y is constant, derivative with respect to x. So what are we going to have? The first term is going to be what? The 2xy. Let me use parentheses here. And then again, y is constant here, and derivative 3xy to the fourth, the x will go to a 1, so that's 3y to the fourth. Let me close the parentheses. And now let's figure out what dx dt is. Well, x is equal to the sine of 2t. So we're going to use the chain rule. Derivative of the sine is the cosine of 2t. But then we have to use the chain rule, and so multiply in front by a 2. Plus, and now we have to get dz dy, and so for that one now, x is constant. So let's go up here to our original function, and I think we're just going to get what? X squared for the first term. The y will go to a 1, and then x is constant. Bring down the 4, that's going to be 4 times 3, that's what's going to be 12x, y to the third, close the parentheses. And then I have to do dy dt. Well, dy is the cosine, so that's going to be negative sine of t, and I don't have to do any more chain rule with that. So that's our whole formula there for dz dt. Okay, now we know that we're going to plug in 0 for t, because we want, our question is find it when t is equal to 0. Okay, so we're going to plug in that 0 for t, but then how am I going to figure out what numbers to plug in for x and y? Well, I want to get a number. Now we're interested when t is equal to 0, so I think you're on the right track. Yeah. See, I want to get actual numbers for x and y, and I'm interested in when t is 0. So for those two functions, I just plug in my 0 for t, and I'll get numbers for x and y. So we want to, what to plug in for x and y? Well, just set t equal to 0 in their function. So therefore, what do we have? X is then going to be equal to the sine of 2 times 0, which is the sine of 0, which is 0. Y is going to be the cosine of 0, which is 1. Okay. All right. So so here we're going to, so for x, here, let's just go up here. For x, we're going to put in 0. For y, we're going to put in 1, 1, 0, 0, and 1. Okay. All right. Well, let me just finish it up on what are we going to get here then? This parentheses is going to be what? I think it's just going to turn out to be the number 1, isn't it? Because I've got 0 times 1 plus 1. 1 to the fourth is, no, 0 times 1, I'm sorry, 3 times 1. So I'm going to have 3 here, aren't I? For that first parentheses. 0, 2 times 0 times 1, plus 3 times 1. So I'll have 3. And then this is going to be what? 2 cosine of 0. Well, that's going to be a 1, right? And then what have I got over here? This one I don't have to do, if I look at this one closely enough, I don't have to do a whole lot of number crunching. We see over here we're multiplying the second term by the negative sign of 0. Well, the sign of 0 is just 0. So that whole second term is all just going to be 0. So basically I just have 3 times 2. So my value here when doing all that plugging in is just the number 6. Okay, you all right with that? Just have to be careful. Okay, now let's look at a second case. I'm going to call this case number 2. And so here again we have z is equal to a function of x and y. But this time around, x and y are a function of two variables instead of just one variable, where x is equal to, say, g of s and t, and y is equal to h of s and t. All right. So let's figure out how things are going to look just by getting a general tree diagram again. All right. At the very top is going to be our top variable, which is going to be z, or we could also have it as the letter f. And now it has two intermediate variables, x and y. So we branch to x, we branch to y. Now let's look at x and y. X is a variable of s and t. Y is also a function rather of s and t. Y is a function of s and t. So under each of the x and y's, I have an s and a t, s and a t. So I have a little bit more complicated tree diagram here. Now let's figure out what these limbs represent along the tree. Okay, here is z and here is x. So this limb is delta z, delta x. Ooh, x. This other limb to the right is delta z, delta y. Now let's look at these. X and s, x and t. So this is delta x, delta s, delta x, delta t. And again, I'm using that delta notation because they're functions of two variables. And then here we have delta y, delta s, and delta y, delta t. All right. So from that tree diagram, I can get the formula then for, let's start with going from z to s. So we were talking about, let's get delta z, delta s. So what we have to do is we have to go through all the branches leading from z to s. All the branches from z to s. So notice we have this branch here, and then we have this branch here, going from z to s. All right. And then if we've written those partial derivatives along there, it's just a matter of just basically writing it off of the tree diagram. So this is going to be delta z, delta x, times delta x, delta s. That's a branch there, plus then delta z, delta y, times delta y, delta s, like that. Okay? All right. And then I just do the same kind of thing for delta z, delta t. This time, though, I'm going to do all the branches from z to t. So start up with z. I've got delta z, delta x. But now I'm going to follow it along this branch, delta x, delta t, plus start up at the top again, delta z, delta y, that way, and then go down that branch, delta y, delta t, like that. Okay. So I'm hoping that, I think that tree diagram is really a clever idea. So let's do an example then with these types of things. So this is a case where we've got functions of two variables. So here's our example. Let's say z is equal to e to the x times the sine of y, where x is equal to s t squared, y is equal to s squared t. All right. So we see here that z is a function of x and y, x is a function of s and t, y is a function of s and t. So from there, you just draw the tree diagram that I had just put on the previous page. All right. So let's say let's find, start with delta z, delta S, okay, and actually let me write down the formula again, and then I'm going to put underneath it what the individual things end up turning out to be. So this is delta Z delta X times delta X delta F plus delta Z delta Y times delta Y delta F. All right. Now let's get these individual things here. Delta Z delta X, okay, we're going to treat Y as a constant, all right? So here's our Z function. So let's see, I think I'm just going to get e to the x sine y. E to the x sine y. Let me just put it in parentheses. Okay, then let's go to the next component, dx, delta x, delta f. So here's our x is equal to st squared. Now in this one, t is going to be constant. We're doing the derivative with respect to f. So t is a constant, so that just becomes t squared. Then let's put our plus. And now delta z delta y. Now this time around, x is a constant. So what am I going to get there? This is what I'm working with. X is a constant. Y is our variable. Yeah. E to the x, that stays there. Derivative of the sine is the cosine. Okay. And then finally, then we do the delta y, delta s. So therefore, delta s, that means, again, t is a constant. So that's just going to be, looks like 2st, right? 2st. All right. So that's what we have there. And frankly, I'm not real concerned with you trying to factor as much as you can to the left. You can do that if something like this is offensive to you and you feel you have to be factoring, but I'm fine with just an answer like this. And now let's also find the other partial derivative. Let's find delta z delta t, and then we'll be finished with this example. So let's again write the formula for that. Now we're going to go down all the branches from z all the way to t, and so we're going to have delta z delta x times delta x delta t plus delta z delta y delta t. All right. Okay. So now it's just a matter, we've got different variables that are being kept constant. With delta x here, we're going to treat y as, again, we're going to treat y as constant. Okay, for that one. So that gives us the same, well, we've already, actually, if we did the first part correct, we can just copy some things down, and we got e to the x sine y for that one. Now, the second part of this we hadn't done yet. Delta x, delta t, that means we're going to keep s as constant this time around. So x is st squared. We're doing the derivative with respect to t. I think we're going to get 2 times st. Right? And then plus, now we already did delta z delta y, and we got e to the x cosine of y. And now we have to do delta y delta t, so we're going to do the s is going to be a constant. So y is s squared t. T is our variable, so that's just going to go to s squared. Okay. All right. Okay. All right, that's all I wanted to do with that particular one. Well, okay. okay, it depends on what you're asked. If you were just asked for delta Z, delta S, then you don't need to do the second part. Okay, it depends on what you're asked for. All right. So the question was, do we always have to put two separate answers? It all depends on what you're being asked. If you're asked for both, then you have to figure out both. Okay. That. And then I guess this would be what I guess would call case 3. All right. So here we have where we have u, say, is a function of x, y, and z, 3 variables, where x is a function of 3 variables, r, s, and t. Y is, let's put G, Y is a function of R, S, and T, and Z is also, let's call it H of R, S, and T. All right, so we've upped the ante a bit here. So let's draw the tree diagram and go from there. All right. So at the very top, we have U, or I could have also put it as the letter F as our function. And now we're going to branch down to 3. So it's going to go to X, Y, and Z. And then for X, we're going to branch to R, S, and T. For Y, we're going to branch to R, S, and T. For Z, we're going to branch to R, S, and T. So we have a lot more, okay, I'm seeing the shaking of the head. We're going to have a lot more branches here, all right? So let's just figure out one of these, okay? Let's figure out delta U, first of all, I need to give you a function, but we're going to do delta U, delta S. So let's give you something to work with here. Let's say that U is equal to X to the 4th times Y plus Y squared Z to the 3rd power, where X is equal to R times S times e to the t. Y is equal to R times F squared times e to the negative t. And Z is equal to R squared times S times the sine of t. Okay. All right. Well, okay, and we're asked to find delta U, delta S. So what this means is we draw the T diagram. It keeps us from forgetting a branch to follow. So we're going to follow from U to S, all the branches from U to S, U to S, U to S. In fact, what I need to do up here is let me put down what these branches represent. This branch from U to X is delta U, delta X. The branch from U to Y is delta U, delta Y, delta U, delta Z, from U to Z. And then along each one of these branches from X to R, X to S, X to T, we again have partial derivatives, delta X, delta R, delta X, delta S, delta X, delta T. Okay? The same thing for Y, the same thing for Z. Delta Y, delta R, delta Y, delta S, delta Y, delta T, delta Z, delta R, oh gosh, delta Z, delta T, delta Z, delta S, T. All right, goodness. Okay, so we want to get delta U, delta S. delta U, delta S. Let's follow the branches here. Let's first go down the X branch. That's delta, so that's going to be, whoops, here we have it. So we're going to have delta U, delta X, and then we go down the branch from X to S, times delta X, delta S. Okay. Plus, now we go down the Y branch, delta U, delta Y, and then from Y to S. Delta Y, delta S. And then finally the third branch from U to Z, delta U, delta Z, times delta Z, delta S. So we have three components here. All right. And so what we need to figure out then, of course, are the individual things. Now, here's our function here. When we figure out now delta U, delta X, now we have three variables here. We have X, Y, and Z. So when we have three variables, we keep the other two variables constant. So this time we're doing the derivative with respect to X, but Y and Z both have to be treated as constant. So Y and Z are constant. All right, so we're careful when we do that, so let's see what we get here. Y and Z are constant, so we go term by term here. X to the fourth is going to become 4x to the third. That Y is just going to hang in there. Plus, and then here, let's see, X, Y, and Z are constant. Ooh, what happens to the second term? It goes away. So we just have, let me put this in parentheses there. And now we have to do delta X, delta F. And let's see, delta F, so that means R and T are constant, the other two. So let's see what we get there. R and T are constant. No, wait a minute. We're talking about here delta X, delta F? Okay, we're doing the derivative with respect to F. So the other two stay constant. You got to be careful. R and T will be constant because we got three variables here, R, S, and T. So R and T are constant. So we look at this thing, R, S, e to the T. S is our only variable. So R, e to the T. S goes to 1. All right. Okay, that's the first term. We do similar stuff with the other two. Now we're back to delta U, delta Y. So that means X and Z are constants. Okay, X and Z. So the first term, X to the fourth times Y, that's just going to become X to the fourth. That stays around, but the Y goes to a 1. And now the second term, let's see, Z is a constant, 2y z to the third. Z to the third sticks around as it is. 2y z to the third, close the parentheses. And now let's do delta y, delta f. Now again, that's delta f, so that means again, R and T are constant. So R and T are constant. If you say that to yourself enough times, it'll sink in. So what are we going to have then for that one?
2RS.
Yeah, 2. Bring down the 2 from the S. 2RS e to the minus T. Okay. All right. We got 2 down, 1 more to go. Let's start over here. Plus, now delta y, delta z. So this means x and y are constant. So let's go back up here. X and y are constant. doing the derivative with respect to z. So that first term is going to go to 0. Second term, y is constant, z's are variable, so it's going to be, bring down the 3y squared z squared. Okay? And then finally, we're down to delta z. What's that supposed to be? Delta z, delta s. Looks like. So, of course, then here r and t are constant. So we look at z here. Here's z. All right, r and t are constant. So I'm going to get r squared sine of t. The s will go to a 1. S will go to a 1, so it's r squared sine of t. Yikes. Okay, there it is. Now, let's suppose, okay, this is what we have here. We do have this nice big formula here for delta u, delta f. Suppose we're asked to find the value of delta u, delta f when, let's see, r is equal to 2, s is equal to 1, t is equal to 0. All right. Now, basically, we do have a lot of r's, t's, and s's in there that we can just plug in. But we also have x, y, and z that we have to find values for. Okay? So how do I find these values for x, y, and z? I'm told I'm interested in specific values for r, s, and t.
Plug in the r into this.
Yes. I'm given, here's x is equal to this, y is equal to this, z is equal to this. Plug in those specific r, s, and t values. So therefore, thus, let's see, x is equal to r times s, so that's 2 times 1 times e to the t times e to the 0 power. So x then is equal to 2, right? Okay. Y is equal to r, which is 2, s squared, 1 squared times e to the minus 0. And that's going to all come out to be equal to 2 also. Z is, well, Z is just going to be 0, isn't it? R squared is 2 squared times 1, but times the sign of 0, so that comes out to be 0. Okay. All right. So we have all these. So let's just plug this in and be done with this problem. Okay. So x is 2, y is 2, z is 0, r is 2, s is 1, t is 0. Now it's just a matter of plugging in. So we have 4 times x to the third, that's 2 to the third, times y, which is 2. All right. R times e to the t, that's 2 times e to the 0 power, which is 1, plus, okay, x to the fourth, that's 2 to the fourth, plus 2 times 2. Oh, then we have a 0, so that's going to make that a 0. And that's times 2 times r times s times e to the minus 0 plus, I love arithmetic, plus 3, I really don't, 3 y squared is 2 squared, z, oh, well, we've got a 0 here, 0 squared, so this whole term becomes 0. 2 squared sine of 0. All right. So this last term is just 0, so we don't have to worry about that. Yeah, what do we have? 4 times 8 is 32. 32 times 4, I think that's 128. All right. 4 times 32, 32 times, yeah, okay. Plus, and then this part was 0. So this is just 2 to the 4th power, right? Oh, yeah, but not this. We've got this here too. So 2 to the 4th is 16, but then it's multiplying 2 times 2, 4. So we have 128 plus 64. So that is 192. All right. So that's our value. Okay, I think this is a good time to stop then. There's one other thing in this section that we'll start with on Friday. It involves implicit differentiation, and then we'll be able to get started on directional derivatives, which is section 12.6. End of story.